stability considerations while designing, then we can avoid this type of failures. Okay, three things are important. You know that. What are the three things are important for you? First, going to build any structures, first you have to make a plan. Either it is a power plant, yeah, either it is a steel plants, yeah, any factories, okay, yeah, any buildings and all. First, you have to plan it properly. What is the purpose of the structures? Based on that, you have to plan. Then each and every components you have to design. Each and every components you have to design. Second, and then later on you have to manufacture, yeah, construct that structures. So while designing, you have to take care of a stability analysis. You have to take care of such that you have to take care about stability such that your structures will not fail due to loss of stability, isn't it? So how to take care? What is the criteria for the stability failures? Okay, that we'll learn in these lectures. Okay, now next, nonlinear stability. So this linear stability, and after that nonlinear stability, this can be called as a buckling and post buckling. Linear stability can be called as a buckling. Your members now it's buckle, and after again you are going to study after buckling, then it is known as post buckling. Okay, so that is also known as a nonlinear stability. So now this is the example. Interesting example is given here. You can see the skin of this aircraft. The skin is now buckled. It is due to compressive loads. What will happen? This deformation takes place. Outer plane means over the skins, and you can see these figures. Arrow I have given here. These members are buckled. So many members are buckled, but still it is in the flying situations. Why? Because your plate and sail panels, skew plates, they have the reserved strength. They cannot be discarded even though buckling. Okay, loss of instability, we cannot discard. To optimal design of this type of structures, aerospace structures, nuclear structures, ship structures, you should have knowledge of nonlinear stability. You should have a knowledge of nonlinear stability because they have the reserved strength. But column doesn't have a reserved strength. Once it's buckle, then you cannot analyze further. But plate and sail have a reserved strength. After that, you can analyze. After buckling, also you can analyze, and that is known as nonlinear stability. Yeah, you can say post-buckling analysis. The next, application of composite materials. This is very interesting because nowadays we want to make your structures becomes lighter. Some of the structures becomes lighter, like which is structure, nuclear structures, aerospace structures. Why we want to make a lighter? Because of fuel efficiency. If it is lighter, then what will happen? Efficiency will be more and less fuel consumption will be there. That's why we remove this conventional materials like steel, aluminum, and all different type of metals. We remove that and we jump into the composite materials. So nowadays, we increasingly using composite materials. So this is the one example I have shown you here. Air application of composite materials. Look at this figure. Then this is Boeing 777. Boeing 777 uses 50% of the composite materials. You look at this 50%. Nowadays, also we are going to increase more composite we are going to use compared to this other like aluminum, titanium, and we try to remove this part, and we slowly we increasing the percentage of composite materials. Airbus uses 53% composite materials. Hello, I'm audible?
Yes, it's fine, fine. Some participant basically. I just muted them.
So now this is the one interesting examples I have shown you: Boeing 777 and Airbus 350, which have the composite materials, uses of composite materials more than 50%. That's why we have to also study about the composite materials. So when I'm going to use a composite materials, then what will happen? Okay, what will happen? Why I'm going to use the composite materials? The strength of the composite materials are more than your conventional materials. A specific strength, a specific stiffness are more, means less weight, high strength. That's why your structure becomes lighter. Okay, when a structure becomes lighter, then what will happen? A stability becomes important for that members, isn't it? Why it is a stability becomes important? Because that members become slender members. Let us consider one plate. Then what will happen when I'm going to use the steel plates? The thickness we need to consider more, but I'm going to use a composite instead of that. Then what will happen? For the same strength, I have to use less thickness. So when thickness will be less, then your member becomes slender. And when member becomes slender, and then we have to see that that member is subjected to compressive stress, is it or not? If member subjected to compressive stress, compressive loads, then there is a chance, there is a probability to buckle. There is a chance of buckling also. There is a loss of stability will take place. That's why while designing, we have to take care of this loss of stability. We have to examine that the structural members should not fail in the stability loss. Okay. So that's why I've given here advantage of composite materials. You see this weight of steel is much higher than composite. A specific stiffness is much higher for composite. A specific strength is also much higher for composites compared to steel and aluminum. And thermal expansions, obviously, it is much less for composite. If thermal expansion would be more, then what will happen? The compressive stress will develop more. When I'm going to use composites in aircraft structures due to solar radiations, the stresses which develop within that panels will be less compared to steels. And when the stresses will be less, then there is a less chance for a stability loss. Okay. So there is a many advantage for the composite materials, but some disadvantage is there. Mechanics point of view is you can say that it is not easier, and it may attack the chemical solvents, and also there is a manufacturing process. Okay, is tedious slightly for a composite material. So some disadvantage is there, but out of that, lot of advantage is there. That's why the popular this composite materials are going to use tremendously. Okay, days to days, increasing the uses of composite materials in different type of structures. So let us first try to understand what is the structural stability, the capacity of the structures to regain its equilibrium configurations. Okay, this is the known as a structural stability. Capacity of the structures to regain in its equilibrium configuration. Next slide will discuss about it. Okay, there is a different type of stability. Okay, so here try to understand two stability cases: a static stability of static equilibrium configurations and a stability of dynamical systems. Means stability becomes important not only static systems, not only under static load, there will be dynamic load also is important. The loss of stability not only due to the compression, due to the static load takes place, due to dynamic loads also will take place. We'll discuss later on. Okay. And next, a stability of dynamical systems. When system is dynamic in natures, like generators, motors, there is a many machinery components which are running. And if you give some perturbation to that members, then we'll see that there is a how much changes in the output. If your output will not significant change in the output, if you are going to give us in you are going to give a small change in input and there will be a small change in output will take place. This means that your dynamical system is stable. If you are going to give a small input and then we'll see that your output changes significantly, then this is loss of stability, isn't it? So according to Lyapunov stability criteria, system is stable if for a small disturbance in initial conditions leads to small change in the response. System is stable if and only if you're giving a small disturbance in initial conditions and there is a change in the a small change takes place either in response, okay, either in stresses, either in the deformations, anything. A small initial change, a small output, a small change in the output. That is known as the system is stable. For conservative systems, they may be stated as equilibrium is stable provided potential energy is positive infinite. So according to potential energy also can be examined that your equilibrium is stable, is it or not. Okay, next slide will more clear about it, about the stability. So now how to define the stability? There is three types of stability we can define. The first, a stable equilibriums. Okay. So remember, now here you look at the first figure, stable equilibriums. Okay. Now your ball is in the hemisphere and just you give a small perturbation to the ball. Then what will happen? It comes back to the initial configurations even after the application of a small disturbance. Very small disturbance you give and you check whether it comes to the original configuration as it or not. If it comes to original configurations, that is known as stable equilibrium. Now the second is a neutral equilibriums. Okay, neutral equilibrium means what will happen? You give a small perturbations, it occupies different positions. Okay, it's shift to the different positions, but it doesn't come back to original configurations. But even though in next positions is a stable positions. So that's why this is known as neutral equilibriums. It occupies new configurations on giving a small disturbance. Now come to the unstable equilibriums. It rolls down the hill after the application of a small disturbance. You look at this. In this hill, what will happen? You give a small perturbations, then it comes back. It never comes back to original configuration, never acquire the different never configurations. It totally fall down from this. So this is the real example I'm going to give. Just you are now standing on valley and mountain where you feel that you are more stable. If you are standing on the valley, obviously you feel more stable rather than you are standing over hill of mountains, isn't it? There you feel less stable. You give a small perturbation there is a chance of instability take place. So this is the three examples. From that you can explain the stability. The stable equilibrium, neutral equilibrium, unstable equilibrium. The three types of equilibrium is there to define the stability. If it is stable equilibriums, when you give a small perturbations like a columns, any structural members, and then you look at this, it comes to original configurations, then these members are stable. And when you give a small perturbation, it's acquire the different never configurations. That is known as neutral equilibriums. And you give a small perturbations, and then you see that there is a large change in the deformation take place. That is known as unstable equilibriums. You can understand from this also. This is your unstable equilibriums, hemisphere. A stable equilibrium, you give a small perturbation here, then it comes back to original configurations. Neutral equilibrium, it's a small perturbation you give, acquire your Okay, it acquires different positions, never positions. That is known as neutral equilibrium. So under two equilibrium configurations of the column under the same loading, there is two configuration possible. Under the same loading, one bent configuration is also possible, one straight configuration is also possible. This will come discuss later on. Okay, this will be more interesting. You can see, whatever you have studied, you can relate with the column examples. Critical buckling load, when the load deformation path bifurcates. Look at this first, this one column, P less than PCR. Okay, second one, P is equal to PCR. Third one, P greater than PCR. Three example I've given to you. Okay, now try to understand this. If the compressive load in a column is coming less than your critical loads, let us critical load is 100 kilonewtons. Now you apply 90 kilonewtons. Yeah, less than 99 kilonewton also you can apply a 10 kilonewton. Any load which is less than 100 kilonewtons. And you give a small perturbation here. Which directions? Lateral directions. What will happen? It will go into different positions, but just you remove that perturbations, it comes to back to the original configurations. Okay, it means that this is your stable configurations. Now, when you apply exactly 100 kilonewtons to the columns, then what will happen? You give a small perturbations, this acquire different dotted configuration, which is nearby. Okay, you remove the perturbations, then it's not come to the original configurations. After removing the perturbations, perturbation means either you give a load, either you give a deformations, but in very small amount. That is known as the perturbations. Very small amount. Just check the stability. Whether it comes to the original configurations, yeah, never comes to the original configuration. Yeah, acquire different configurations. That you have to check. How to check that stability? While giving a small perturbations, either small deformations, yeah, small velocity, a small load, anything you can give in terms of perturbations. So now second example, you give a small perturbation here, what will happen? You look at this, it's acquired different dotted configuration which is very nearby, isn't it? That is neutral equilibriums. But when P greater than PCR, then you see that very small perturbation if we give, then large deformation takes place. Means this now it becomes buckle. Okay, the third one is loss of instability takes place. Okay, so now to plot this here, you can see that primary load deformation path before buckling. You can look at the right side figures. Okay, in this figure, you see this, the dotted line is coming up to this. Means you apply load 0 kilonewtons, nothing will happen. 10 kilonewton, nothing will happen. You just deformation becomes 0. Out of plane deformations becomes 0. Again you apply 0. Again you apply 0. You reach to the 100 kilonewtons. Then what will happen? Deformation still 0. But when you increase more than 100 kilonewton, you look at this. Even though increase 1 kilonewton, 2 kilonewton, 3 kilonewton, means extra 5% of the load, then see the deformation is large. Delta is very large. So once it's buckle, this point is known as a bifurcation points where the out of plane deformation takes place. That point is known as on the y-axis, in the load axis, is known as bifurcation points where the graphs is your structure is going to bifurcate. That's why it is known as bifurcation points. And this path is known as post buckling path. This path is known as buckling. Okay, so this bifurcation point is known as buckling of the structures. So this point is bifurcation. So this, if you are going to calculate this loads, that load is known as buckling loads. So this path is known as a primary path, which is stable path, and this path is secondary path, which is a stable or not a stable, unstable. That you have to check, okay, by some of the examples. So I am going to discuss later on, and then we'll see that this path is stable, is it or not. So now this column examples you can relate with this one. Okay, stability of structures. The unstable equilibrium, is the right side, stable equilibrium, the left one, and neutral equilibrium, the middle ones. So this example you can relate with the column examples. So now is it clear to everyone what is the stability?
I hope you explained it very clear. Very understood.
Okay. So what is the stability? Is it clear? Stability is the capacity of the structures to regain its equilibrium configurations. So now any structure is in equilibrium configurations, but I don't know whether that structure is stable or not. So how to check the stability? You have to give a small perturbation to that structures. Okay, and they see that response. Okay, response. If you see, it comes deformed. Okay, giving a small perturbations, your slight deformations will take place, but comes to the original configuration again. Then you can say that that structure is stable. But if given small perturbations, it acquires new configurations which is adjacent of that, that is known as neutral equilibrium. But you are going to give a small perturbation to the any structures, and then you see the large deformation takes place, then what will happen? That is unstable equilibriums. Okay, means loss of stability takes place. Means now structure no more stables. Large deformation takes place means what will happen? Your stresses deform due to deformations. You calculate the strain, and due to strain, you calculate the stress by constitutive matrix. So you calculate the stress, isn't it? And then these stresses you have to check with the yield stresses of the materials. And then you'll see that obviously, if a large deformation will be there, large strain will be there, and large strain due to large stresses obviously will cross the yield stresses of the materials, means your system will collapse. Is it clear? So there is a many types of failures. I am going to discuss about the structural failures. Okay, which is due to loss of stability. One failure is the material failures. Okay, now their material failures here. A structural failure means it is not necessary your stresses will within that member crosses the yield stress of the material. Before that, also there is a chance of failures, isn't it? That is very important. And where this occurs, when the member is large. Then when you have a large member, there is a chance of buckling will take place, loss of stability will take place, even though give a very small compressive loads, even though you have very small compressive loads, then there is a chance of there is a loss of stability take place. But due to the small compressive loads, what will happen? The stresses will be less. It is very less than your yield stress of the materials. But what will happen? Before crushing of the materials, there is a buckling takes place. Loss of stability takes place. That's why the stability is also important for a study. And while designing any structural members, you have to take care of stability also. Why it is important? Now you have learned. There is a many types of failures I have shown you, which is gives a motivations to avoid this type of failure in the future. And for any structures, when you are going to build your manufacturing, that first you have to plan properly, then design it. While designing, you have to take care of stability. Okay, loss of stability. Then how to take care of that? Then first you have to estimate the loads. What type of load is coming on that structures? And whether that load is compressive load is it or not. Yeah, bending is there, the compressive load is there, yeah, dynamic load is there, static load is there, types of load you have to estimate there. Any member, if it is subjected to compressive loads, whenever we have tensile loads, there is no problem in the stability. Wherever the member is subjected to compressive loads, that you have to take care of that. Okay, so then that members you have to see whether this member is stable, is it or not. So how to improve that loss of stability, means how to avoid that loss of stability? Just to increase the thickness of the members, yeah, give us some stiffener to that members is at discrete locations to avoid this phenomena. Okay, so first you have to find the load. while designing how much load is coming to the structures, and then due to that loads, stresses you have to find, and then this will, then we see that how to check the stability. You give a small perturbations and then see that whether it comes to original configuration, is it or not. It comes, it's okay. It's not come, then you have to take care of that, isn't it? Then you give some stiffness, thickness you increase such that they able to take that amount of loads. So you can able to avoid using that concepts. Okay. So next slides, I'm going to discuss. Now, I hope so it is clear what is the stability. So this is some example I have given. You look at this column examples. One side is roller, one side is hinge. You give a small, okay, no, you give a load PS, which is static loads. Now I'm going to give a static, completely static load here. Then what will happen? This members is going to deform from C0 to C1 when loading comes from A to B. When load comes from A to B, then these members deform from C0 to C1. Then what will happen? And this deformations totally depends on the what? The amount of loading applications. Means depends on the PS. Now you see the another examples. The static instability means your load is static, not time dependent. Dynamic instability means your load is time dependent. Okay, the many structure is subjected to time dependent. The second example I have shown you, Tacoma narrow bridge. Tacoma narrow bridge is subjected to the wind loads. Wind load is dynamic in nature. Okay, and due to that, what will happen? The large oscillation takes place of the bridge. Means the frequency of the loading, wind load, coincide with the frequency of the structural members. Then once your frequency coincides, you know that there is a large deformation will take place. And once your large deformation will take place, then there is a huge chance of collapse. The second example, I'm showing that dynamic instability. You can second figures, which is correspond to dynamic instability. Their load is static plus dynamic in nature. Means PS is a static load and PD into cos delta T, cos omega T is a dynamic in nature. Okay, dynamic loads. So this is the combination of static and dynamic loads. Then what will happen? Your maximum value is PS plus cos omega T is maximum value 1 and minimum value -1. So what is the value of P of T? PS plus PD, PS minus PD. So now the members, okay, the hinge locations shift from A to B, then C0 moves to C1. Because of dynamic in natures, what will happen? B again will go to A place. Then C1 moves to C0. And then momentum in this left directions, then what will happen? C0 go to C2 when A reach to the B points. Then again C2 reach to the C0, then B moves to A. So now to complete one cycle, you look at this. C0 moves to C1, C1 to C0, C0 to C2, C2 C0. So complete one oscillations. This column complete one oscillation in transverse directions. At that time, a load complete two cycle. Why? Because A to B, B to A, then your members C0 to C1, C1 to C0. Okay. Again, A to B, B to A, the members shift from C0 to C2, again C2 to C0. Then it's complete one cycle. Your members in the transverse directions complete one cycles. That time your load complete two cycles. So when loading frequency is twice, then your structural frequency in transverse directions, then what will happen? Your dynamic instability will take place. Then dynamic instability, when I'm talking, means its large deformations will take place. Not only under static loads, your structural members may collapse. Your structural member may collapse due to dynamic load also. Okay. And this dynamic load may be very less. Is it not necessary? It is, you have a high dynamic load, then there will be chance of buckling. Even though very small dynamic load, but the frequency becomes matters. frequency of the loading is becomes twice than a structural frequency of the structures, and load is magnitude is very less, then also the structures will collapse. I'll discuss about the dynamic stability later. It is very interesting topic. I'll discuss. Okay. Now another example, dynamic pulse bucklings means here load is very short durations. Okay, the like impact loads, which is known as a pulse loads, sinusoidal, triangular, and immediate it will be act and then vanish. Then what will happen? Then there is a chance of buckling will take place. You look at these diagrams. It because it is not monotonic in nature, means continuous natures, because it is the second one load is the continuous. The third one load is the impact. Okay, short durations. That's why this load is expressed in terms of TS. TS is the duration of the shock. It is 0.1 second, 0.01 seconds. It's very less time, isn't it? Then the magnitude is becomes very important. If you apply these loads, very short durations, if your intensity of the load is not high, then there is no chance of buckling. Okay. Then even though very short duration of loading is there, but intensity of the load is very high, then what will happen? The member will buckle. So this diagram have shown that dynamic pulse buckling. Okay, bifurcation points and limit point. What is the difference? That I have discussed already. Bifurcation points. Stability becomes important for the slender structural elements. When you have slender structural elements, slender members, then there is a chance of stability loss. I have discussed. And why it is important? Because nowadays I am going to shift in different materials like a composite materials, functionally graded materials, which have the higher strength, specific strength compared to steel and aluminum. That's why for keeping the same strength, thickness I can reduce, because getting the same strength, that's why we can reduce the thickness. Once you reduce the thickness to save the materials, and it also becomes lighter weight, to increase the efficiency of the fuels, what will happen? The thickness becomes lesser than A by H ratio. If you take a plate, and if you consider a plate, then what will happen? This is your A, and thickness, this is your B. So what will happen? A to B, A to H ratio is large. Let us A by H ratio is equal to 100, yeah, more than that. It means that these members become slender. And when you subject it to compressive loads, any type of, either it is parabolic, different type of non-uniform loads, it comes from both sides, then this plate will deforms abruptly. Out of plane deformations will take place, isn't it? So this plate will go either inside, yeah, outside of this desktop, isn't it? It means that it deforms out of plane due to the not sudden, due to the applied non-uniform, yeah, uniform loads. Okay, so this is known as a buckling. So this buckling is very important for the cylinder members, isn't it? Not when you have not cylinder members, is thick. If you consider A by H is equal to 5, then it is very thick. Then this will not fail due to the compressive loads. It's not fail. It will may crush. It not loss of stability takes place, because this A by H is equal to 5, 2, 3 is a not a cylinder members. Okay, so when you have a cylinder members, then you have to study about the loss of stability. And nowadays the members becomes thin and thinner, because of why? Because of to increase the efficiency, increase the efficiency of the members, light to bring to create to manufacture lightweight structures, such that it increase the fuel efficiency. That's why it is this bifurcation, this stability becomes important. If you look at the long back in 16th century and 17th century, there is no important stability, not that much important. Why? Because earlier the structures was the size of the structure was used, which is made of either rock, yeah, either column was used, that there is no loss of stability, that we don't concern about the stability. Okay. Previously, there is no issue about the stability, but nowadays in modern structures, we concern about the economical. When I'm going to economical designs and optimal designs, then obviously we have to save the materials, and automatically your structure becomes thin and thinner and slender. And when structure member becomes thinner, then we have to study stability and see that whether that structure members will there is any loss of stability, is there, is it or not. Okay. So here instability can lead to catastrophic failures, must be accounted in design. Bifurcation point and limit point, there is 2 points you have. Okay, what is the bifurcation point and limit point, we'll discuss. Post buckling, you know that study of the behavior of the structure after buckling. Once it's buckle, and then again plate and cell have a reserved strength. The structural member, some of the structural member have reserved strength. And to design, because designers always wants to design optimal designs, and for optimal designs you have to know the reserve strength. When exactly we utilize that material capacity after buckling also, that's why we have to analyze the structures even though after bucklings, that is known as post bucklings. Plate and cell have found the carry load even after buckling, that is known as reserve strength. If you look at this post buckling equilibrium path, I have shown you. This is a plate subjected to uniform loads. And if you want to plot the load deformation path, then we'll get, it may be bifurcating the out of plane directions, either inside or outside. Then what will happen? There is 2 diagram we'll get, this and this. And this load magnitude is very less. We'll start from this. Keep on increasing your load. There is no what will happen? Give a small perturbation. There is no change, no out of plane deformations. Again, you increase loads. Again, you give a small perturbations. There is no change in the deformations, and reach to the bifurcation points. Once they reach to the bifurcation points, means P is equal to now becomes P critical. Correct. Once you reach the P critical, means buckling loads, what will happen after that? You give a small perturbations in out of plane directions, then there is some deformations will take place. You keep on increasing loads, deformations will increasing. You see that, and it is symmetric. That's why left side as well as the right side deflections will in both directions will be there. This W naught minus and W naught plus is the imperfections, because no structures will be perfect. Some imperfection will be there, either from manufacturing sites, yeah, from the using transportation from one place to another place. Some deformations will take place. Okay, some imperfection will be there in that structure. So when you have imperfection, what will happen? When you apply compressive loads, then due to that imperfections and due to that axial loads, there will be moment will develop. So as soon as load will apply, then what will happen? You look at this. As soon as load will apply, then start bending takes place. Okay, this is the for perfect columns, perfect plates. When you have perfect plates, then there is no change in the outer plane deformation up to bifurcations. Once it's bifurcations, means buckling take place, then you increase your loads, then your deformations will be there in out of plane directions. But when you have imperfections from the initial, some imperfection is there, then what will happen? As soon as load will apply, then it will bend, and you will get this type of graphs. And imperfection intensity will be increases, then you see this graph will be there. Okay, this is the negative imperfections, and this is the positive imperfections. And this is post buckling equilibrium path for the panel. So this is your post buckling equilibrium path for panels, and you see this. If you go upward directions, then this diagram will be there. When you go downward directions, you will obtain these diagrams. This load deformation path due to axial loads. Due to axial loads, this member panels will go out of plane directions, either upward or downwards. But when it is complete perfect, then what will happen? There is no out of plane deformations will take place. From here to here, we'll go straight up to bifurcations. And then we go up, depends on the perturbations. I'm going to give a perturbation in upward directions, then we will go up these directions. And when I'm going to perturbation downward directions, this will go like this. So this is your post-buckling equilibrium path. When you have imperfections, positive imperfections, then you have this path. When you have a negative imperfection, then you have. So this is not symmetric figures for cell panels. But when you have a plate, then you have the symmetric figures, isn't it? So this post-buckling equilibrium path for different type of loading, heating, everything I have given here. This is for plate, this is for panels. Okay, for a different uniform loads, localized load, localized heat. I'm not going to discuss now details. Static stability for a plate, you see this load deformation path. This point is a bifurcation point, but you see the column. Column now it's almost buckle. Once it's buckle, they don't have reserved strengths. That post buckling analysis is not important for the columns. Okay, but for the plate have a reserved strengths, then post buckling equilibrium is important. And then you want to examine the failure, then every deformations you find the stresses, and stresses crosses yield stress is it or not. Then some places will get here, now it becomes collapse. Okay, so now more than 3 to 4 times, yeah, even though more than that, your plate will completely fail. Not exactly at the buckling load, it fail. This is the 2-bar frame. This is the post-buckling equilibrium path. This is for a spherical cap or arches. You have, this is the type of post-buckling equilibrium path. For cell panels, this is the post-buckling equilibrium path. This is known as a snap-through graph. This is known as a snap-back graphs. And this path you want to plot, you have to have used the arc length methods. One method is there that you are going to use and to plot this path. Okay. There is three types of approach is there to plot this path. Either load control, displacement controls, and then load control, displacement control, and one is the arc length methods. Load control means load you are going to control and try to plot the deformation. Displacement controls, you are going to give a deformations and then you are finding the load. So in laboratory, for UTM dynamic actuators and all are there, you already maybe performed some test. Then that load is the displacement type of loads. We are going to give a displacements 1 mm, 2 mm for a 1 minute, 2 minutes like that. Okay, so that displacement you are going to give and then try to find the load corresponding. So load deformation path, if we cannot plot using the load path. Okay, load control approach. We can plot this path using the displacement control. We can plot using the displacement controls. Okay. This is the hinge cell panels. This we can plot by using the arc length approach. Okay. So the method of stability analysis is a bifurcation approach, energy approach, dynamic approach. There is 3 types of approach in there. Bifurcation approach means consist of writing equation of equilibrium. We used to write a equilibrium equation and try to solve that. Okay, and to find the buckling loads. Energy approach, we obviously we have to write energy, total potential energy of the system we need to write, and then you have to examine the stability of equilibrium state using the energy approach. So to rewrite the energy, not equilibrium. Dynamic approach, writing the equation of dynamic equilibrium of the system, solving the equations to determine the natural frequency of the systems, and instability correspond to the reduction of natural frequencies to become zero. So as your compressive load will increase, then what will happen? Resultant stiffness will reduce, and when your resultant stiffness will reduce, then your corresponding frequency k is equal to m omega square. Your frequency also will reduce. So at critical loads, theoretically, your frequency becomes zero. A stiffness becomes zero means frequency becomes zero, isn't it? So there is 3 approach. Mainly, we are going to discuss about the bifurcation approach and energy approach. We'll solve some problems and find we'll solve some problems and solve bifurcation approach and energy approach. Okay, using both the approach. Mainly we are going to deal with the bifurcation approach and energy approach. Okay. And later on, I'll show that some dynamic approach also, some loss of stability using the dynamic approach. So now I'm going to take a very simple example. Using bifurcation approach, we want to solve these problems. Okay. So one rigid bar you consider, which is subjected to P load here. And this rigid bar is rotationally restrained using rotational spring. So this rigid bar is supported at the one end using the rotational spring, other end is applied loads. Please try to find the critical loads. P is equal to PCR. I need to find how much buckling load will apply such that it suddenly will go into the deformed state. What will be the value of P such that it suddenly will go into the out of plane deformations, suddenly will deforms. Okay, but when you apply P load which is less than PCR, then what will happen? Nothing will happen. The compressive load will be increases. That's all. There is no any deformations will take place in these directions. Yeah, in these directions, no deformation will take place. Okay, so now how to find the critical loads? How to find the buckling loads? There is a one way. Using bifurcation approach, and another way is energy approach. So now we'll solve these problems using the uh, bifurcation approach. So now look at this bifurcation approach. You just give a small perturbations here in the deformed state, just to analyze how you have analyzed the stability. Just you give a small perturbations. It's what will happen when you give a small perturbations means small rotation. Perturbation means I am going to give a small rotation because you have a rotational spring. So I am going to give a small rotation. Then what will happen? What will happen? This will reach to the these points. Okay, these members will reach to these points, and the theta is very small. And then we'll see that this members comes to the original configuration, is it or not. If it comes to original configurations, this means that your P less than PCR. Okay, if P exactly PCR, then this will be remain as deformed state. So now to find this, assume a deformed shape that activate all possible degree of freedoms. You see this, what will happen? This is your L, and L length is this, then projection is L cos theta. Then this change is how much? L1 minus cos theta. Okay. And this length is how much? From here to here? L sin theta. Okay. So now theta, if you give a small rotations, a small deformations, then this load moves from here to here, L sin theta. So now please take the summation of moment, because these members will be in equilibrium in even though deformed state. So how to examine the equilibriums? Take a summation of moment about these points. Okay, take the summation of moments to be zero. The equation of a static equilibrium in the deformed state, you need to write the summation of moment to be zero, and you apply the summation of moment here. What will happen? P load is there in these directions, and R is the L sin theta. So R cross F will be like this, isn't it? R cross F is like this. Is it clear? Which is anti-clockwise. Now, anti-clockwise is a PL sin theta. But you look at this, K into theta is a clockwise rotational spring. Develop the moment, K into theta, which is the clockwise. So minus K theta is clockwise, which is negative, and anti-clockwise PL sin theta 0. So P is equal to, you get K theta divided by L sin theta. For small deformations, I discussed, we give a small perturbations. A small perturbations means very small deformations. So sin theta now becomes theta. Sin theta क्या हो जाएगा तुम्हारा? sin theta theta के बराबर हो जाएगा. Now please substitute in place of sin theta, theta will cancel, and PCR becomes K by L. So what is the critical load? K by L. If you apply load P is equal to less than K by L, then what will happen? It comes to the original configurations. If you apply load P greater than K by L and you are going to give a small load, then what will happen? It deforms very large, isn't it? The deformation will be large. Okay. 1 second. Okay. Let us start. First example I have taken as a rigid bar. One end is rotationally supported. Rotational spring is applied at left end. Right end is free. Only load is applied. Okay. Now let us check the stability of this and try to find what will be the critical load using bifurcation approach and energy approach. I am going to discuss mainly these two. Bifurcation approach, obviously equilibrium. We need to write a equilibrium. Energy approach, we need to write a energy. So is it clear? Okay. So now equilibrium, how to establish summation of forces to be zero, summation of moment to be zero. You know that. You know that, isn't it? Now at this example, the first examples, what I have chosen, using bifurcation approach, try to uh, write the equilibrium in the deformed state. Solve the stability problems I discussed. Always you have to choose in with either energy, yeah, either equilibriums, okay, static equilibriums in the deformed state. So you keep in mind in the deformed state, because you are going to give a perturbation and then you are checking whether it is stable or not, whether system is stable or unstable or neutral. You want to check by giving a perturbation. So perturbation we are going to give means you examine the stability in the deformed state. If it comes back to original configuration, is stable, it's never comes to original configuration, remains in the same configuration, that is neutral, and you give a small perturbation and large deformation takes place, then it is unstable. So now is it clear about this concept? So now using bifurcation approach, we try to write the static equilibriums in the deformed state about the left points. Okay, left point let us consider A and right is B. At the left points, yeah, origin you consider at this summation of MO is equal to 0. So now K theta we use it coming from the rotational spring, translational spring. What is the moment? Force will be the deformations K into X, isn't it? But here rotational spring you have, that's why K into theta, the moment directly will get. And when you have a translational spring, then K into deformations will get the force. Rotational spring में directly K into theta will be the moment. So minus K theta in the clockwise direction, PL sin theta in the right, in the anti-clockwise directions. So now you please find the p value. P value is coming K theta by L sin theta. For a small deformation, I told you I have to check the stability. For a small deformations, buckling if you want to find, a critical load you want to find, means you have to check for the small deformations. A small deformations, you know that sin theta is equal to theta, cos theta is equal to 1, tan theta is equal to theta. Please substitute here, then you are able to get what is the critical loads. The structure will be in a static equilibrium in the deformed state at P is equal to PCR is equal to K by L. If you applied load is less than K by L, means even though give a small perturbation, theta will be very small, it comes to back original configurations. If exactly you apply PCR and you give a theta, then your member will be remain in the theta deformations. But when P is greater than PCR and you give a small deformation theta, then your large deformation will take place, means more than many times more than theta, isn't it? So when P less than PCR, the structure is not in the deformed state. Look at this. It's a statement. P less than PCR, a structure will be not in the deformed state. The structure will buckle into the deformed state when P is equal to PCR. The example, second example I have taken. Let us see this. Same rigid bar you have. Left end is the hinge. Right end is supported by translational spring. Previously, it is rotational spring at the end, left end. Here, I have considered translational spring at the right end. Now, please again solve this problem by bifurcation approach. You need to take a moment about this O. What is the moment? You give a small deformation first. Means a small deformation. How you are going to give? Very small theta I am going to give. You look at this. Very small theta. Now it comes to deformed configurations. Deformed configuration means all possible degree of freedoms you have to activate. That is the meaning of the deformed state. Now, obviously, this is the theta. Then what will happen? This will be L sine theta. This will be L cos theta. Then this, obviously, the positions of this and position of this, the difference will be L into 1 minus cos theta. A spring, how much is going to elongate? KL, because K is the spring constant, and this is how much is going to elongate, means going to up by L sine theta. Then force which is developed, how much? K into deformation in the spring, which is L sine theta. So K L sine theta is the force which is acts along these directions. Going to up means the compressive force will develop in the spring, which is equal to K L sine theta. Now you take a moment about O. So K L sine theta, and how much distance? L cos theta. This is nothing, it is L cos theta you multiply. Okay. L cos theta. But for a small deformation, cos theta becomes equal to 1. So now minus KL sine theta into L cos theta plus PL sine theta due to axial load, PL sine theta. So this is the equations we will get. A steady equilibrium about O in the deformed state. And please solve this. P is equal to KL square sine theta by L sine theta. For small deformations, what will happen? Sin theta is equal to theta, cos theta is equal to 1. Then PCR will get K into L. Thus, the structure will be in a static equilibrium in the deformed state. P is equal to PCR is equal to KL. When P less than PCR, the structure will not be in the deformed state. The structure will buckle into the deformed state when P is equal to PCR. Isn't it clear now? Two example I've shown you using bifurcation approach. These two same example I'm going to solve by energy approach. Okay, the energy approach will currently look at the use of energy method for elastic system subjected to conservative force. Total potential energy we try to find. Total potential energy is what? Total potential energy, strain energy of the system due to deformations and due to the load. What is the work done? Okay, this work done is negative, work done on the system. That's why it is negative. The total potential energy will be equal to strain energy of the systems minus external work done. Okay, so please try to find the total potential energy, and this total potential energy of the systems must be stationary. For that, first derivative of the pi must be equal to 0. तो मुझे क्या करना है? Del pi by del theta to be equal, because theta is your degree of freedoms. So based on this, del pi by del theta to be 0 for a stationary configuration, for equilibrium configuration के लिए मुझे क्या करना पड़ेगा? Differentiate करना पड़ेगा. That will be equal to 0. And stability check करने के लिए क्या करना पड़ेगा? Second derivative we need to calculate. Okay, second derivative of total potential energy. And second derivative, if you are getting greater than 0, then your function is stable. And if it is less than 0, this is unstable. And you know this is this concept. How you know that? How any function you have considered, and to find the maximum value of the functions, what exactly you are doing? You're differentiating the function with respect to the variable, and then making it to 0 and finding the value of variable, again calculating the second derivative and substituting that variable values which you got it from the first derivative, make it equal to 0. Substitute in the second derivative. If you are getting less than 0, then what is the solutions? If it is less than 0, then whether you will get a maximum or minimum. Please, anyone?
Maxima.
Yes, if you are getting less than 0, then it is maxima. And if you are getting greater than 0, means minima. And what for the stability? These two example I'm showing. The ball on the heel of the top and ball here is in the hemisphere at the bottom of the hemisphere. This is the minimum, yeah, maximum. Which one is the minimum? The left one is the minimum. Okay, minimum energy associated with that. This one. And your minimum energy associated means you have the stable configurations, a stable equilibrium. And this is your maximum energy associated means what will happen? This is the unstable equilibriums. Now from this you can conclude that your for a stability, what will happen? Del square pi by del theta square supposed to get less than 0. If I'm coming less than 0 means minima. Minima means a stable equilibriums. Is it clear? Then another example. So obviously one person is standing and one person is sleeping, then what will happen? Which will feel the stable? The person which is in sleeping, that feel the stable. It means that minimum energy associated with that person's. That is the same thing concept. So for stability, your minimum energy supposed to be associated with the stability. And when you have unstable means maximum energy associated with that. So second derivative, you have to find it to examine whether system is stable or not. If it is stable, means second derivative supposed to be get greater than 0. If it is coming greater than 0, means you have a stable configurations. If it is coming less than 0, means unstable configuration. If it is coming 0, means intermediate. We cannot give a comment. Then what will happen? We need to find again third derivative, four derivatives, and which derivatives will come first. Greater than 0 means stable, less than 0 means unstable. Okay, we are going to discuss this one. The energy method is the best for establishing the equilibrium equation, examine its stability. You can see these examples. Rigid bar supported by rotational spring here. You have written deformed state. And please find the energy. Write the equations representing the total potential energy of the systems. What will be the total potential energy of the system? Strain energy क्या हो जाएगा? Strain energy हो जाएगा half k theta square. Half k, because of rotational spring, the energy will be half k into theta. Half k x square. Okay, that is the energy now associated with the spring. The half k theta square. And work done is how much? Work done will be force into deformation in that directions, in the direction of force. This is your axial load supplied in this directions. How much deformation takes place? L into 1 minus cos theta. This deformation takes place along these directions. You look at this. This points moves here, and then this deformation is L into 1 minus cos theta. So what is the work done? P into force into displacements. Force into displacements mean P into L into 1 minus cos theta. The total potential energy need to calculate half k theta square minus PL into 1 minus cos theta. So make it stationary first. What you have to do? Just to find the first derivatives of the total potential energy, and then first derivative will get this. For equilibrium, what will happen? Del pi by del theta is equal to 0. Therefore, k theta is equal to minus PL sin theta. You look at this for equilibriums. Del pi by del theta is equal to 0. Once you differentiate this, you will get this. And for small deformations, sin theta becomes theta. And finally, you will get buckling load. PCR is equal to K by L. So you, by energy approach also will get the same solutions which you got already in the bifurcation approach. Okay. Energy method predicts the buckling will occur at the same load PCR as the bifurcation analysis methods. At PCR, the system will be in equilibrium in the deform. Examine the stability. At PCR, system is in equilibrium, but that equilibrium is stable or not, that will be decided based on the higher order derivatives of the potential energy. Examine the stability by considering further derivative of the total potential energy. This is the small deformation analysis. Theta tends to be 0. So please you see this. 1 half k theta square minus PL 1 minus cos theta. First derivative is this. Then second derivative coming as k minus PL. So now from k minus PL, when P less than PCR, so this is your when P is less than PCR. P का वैल्यू कितना आ रहा है? K by L. P का वैल्यू K by L से थोड़ा सा कम होगा तो क्या होगा? ये तुम्हारा सेकेंड ऑर्डर डेरिवेटिव ग्रेटर देन 0 होगा. So that is your stable equilibrium. P greater than PCR, then second order derivative less than 0. This is unstable equilibrium. When P is equal to PCR, then P is equal to exactly PCR के बराबर होगा तो second order derivative becomes 0 हो जाएगा substitute करने पर. So we cannot say that exactly PCR whether it is stable or unstable. Okay, that we need to check. Energy approach, small deformations. This is your stable from up to bifurcation points, exactly at bifurcations, intermediate, and after that it is unstable. According to the small deformation theory, you are able to conclude these diagrams. A stable, intermediate, unstable. A stable means del square pi by del square theta less than 0, del square pi by del theta square exactly PCR 0, and del square pi by del theta square greater than 0. It is unstable when P greater than PCR. Okay, so now second examples, first example I'm going to solve by large deformation analysis. Large deformation means I cannot take sin theta is equal to theta. Is it clear? I cannot take tan theta is equal to theta and cos theta is equal to 1. I cannot take large deformations because large deformation is very important to plot the post buckling analysis, post buckling path. Small deformations to find the critical loads. But large deformation analysis, we able to plot the path after buckling, which is known as post-buckling analysis, known as non-linear stability analysis. Is it clear? So now, large deflection analysis, rigid bar with rotational spring. Pi is equal to U minus WE, half K theta square. Work done is equal to PL 1 minus cos theta. You know already. The potential energy, you find it, differentiate, then you will get this. For equilibrium, this will be equal to 0. Therefore, is equal to K theta is equal to minus PL sin theta. But I cannot write sin theta is equal to theta, isn't it? So P is equal to K theta divided by L sin theta for equilibriums. At equilibrium, what you got? What is the axial loads? Axial load is coming K theta divided by L sin theta. So now please try to plot P and theta. Post buckling P and theta relationship is given above. If you are going to plot these equations, P is equal to K theta divided by L sin theta, then you will get this. After plotting this, K by L is nothing, it is what? PCR. So P divided by PCR is equal to theta divided by sin theta. When you are going to plot this, so this diagram will get. So different theta, sin theta you calculate, you will find the ratio, you will get this. So this is the diagram we'll get. Okay. P by PCR is equal to theta by load P by PCR this side, and this is your theta. With respect to theta, you plot these equations, you will get this path. So this is nothing, it is a post buckling path. Okay. So energy, now we need to check this path is stable, is it or not? How to check it? I'll let you know. Large deflection analysis, examine the stability of equilibrium using higher order derivative. Okay. Large deflection analysis, examine the stability of equilibrium using higher order derivative of pi for large deflection analysis. So now P is equal to K theta by L sin theta. Again, you substitute back in these equations. You see this again, this equation I'm representing here after substituting the value of P is equal to K theta. Again, you substitute this. This will get del square pi by del theta square is equal to K 1 minus theta by tan theta will get. Now, this is always all value of theta. Theta by sin tan theta is always less than 1. Any value of theta you consider, theta by tan theta is coming less than 1, then what will happen? This is always positive. Okay, this is always positive means a stable. But exactly at the theta, what will happen? This becomes as 1. So this now, this will becomes equal to 0. Exactly theta kya hoga? The second order derivatives becomes equal to 0. Now, now it is at theta, I am not able to find whether it is stable, unstable. Okay, then how to find it? Exactly at theta. So now you find the, just take a second order derivative at theta is equal to 0. Second order derivative of pi is equal to 0. This is inclusive, means Taylor series expansions you have to perform for a potential energy at theta is equal to 0. Clear? So Taylor series expansion is this. Pi is equal to exactly theta is equal to 0, del pi by del theta into theta half 1 by root 2 del square pi by del theta square. So just this is nothing, it is Taylor series expansions. And please try to find this Taylor series expansions first non-zero term of pi. Once you expand it, what is the non-zero terms? At theta is equal to 0, you look at this. Theta, when you substituting 0, then what will happen? Cos theta 1, 1, 1, 0, and here theta is 0, so 0. Okay, so non-zero term I need to find, non-zero. Okay, the del pi by del theta you find. What is the del pi by del theta? This, again you substitute theta is equal to 0, then this becomes 0. Again del square pi by del theta square, again you find it, you look at this, at theta is equal to 0, 0. Then third derivatives, PL sin theta, again theta is equal to 0, then PL sin theta becomes 0. Then fourth derivative, PL cos theta, and theta is equal to 0, then this becomes as PL. So fourth derivatives is equal to P into L, which is known as K, where K is greater than 0. So this means first non-zero term is greater than 0. It means that state is stable at P is equal to PCR and theta is equal to 0. Even though your system is stable at critical load PCR and theta is equal to 0. Okay, because first non-zero terms is coming greater than 0. If first non-zero terms, if suppose less than 0, then you can say that this is unstable at critical load. So before critical load is stable. Before critical loads is the stable. After critical loads is the post-buckling path, and from this is coming stable. And exactly at the critical loads also stable. It means that this point is also stable, this path is also stable, and this primary path is also stable. The secondary path is also stable. You look at this, this is known as secondary path and this is known as a primary path. The primary path is also stable because P less than PCR, and for a small deformation theory you can find it. And P greater than PCR, then you have to use large deformation theory, and from there you check whether it is stable or not. P greater than PCR. Okay, so this is the stable, and exactly theta is equal to 0 and P is equal to PCR. You have to check with the help of Taylor series expansion. First non-zero terms coming greater than 0, that's why it is stable. Now energy approach by small deformations. Rigid bar supported by translational degree of freedoms, a spring at the ends. You look at this. This is the examples. I am going to write energy of this. So first you have to, what you have to do, just to give a perturbation here. A small perturbation means theta, and then activate all the degree of freedoms and draw free body diagrams. And once you draw, then you try to write energy. So what is the energy? Energy of the equations will be equal to strain energy of the system and external work done. You subtract these two, then you will get total potential energy of the system. Total potential energy you need to find every time. And your energy, strain energy is how much? A spring is going to elongate by KL sin theta. So half KX square, L sin theta whole square. And theta is very small, small deformation I'm talking. Then what will happen? KL square theta square. What is the work done? Work done is PL 1 minus cos theta. So total potential energy you write half KL square theta square minus PL 1 minus cos theta. Then del pi by del theta is equal to KL square theta minus PL sin theta, isn't it? First derivative you need to find now, and this make it 0 for stationary. Then you are able to find relations, and for theta is very small, from there you are able to get what is the critical loads. So using bifurcation approach you got the same solutions. PCR is equal to K into L. Okay, the energy method predicts the buckling. Energy methods predict the buckling will occur at the same load PCR as the bifurcation analysis methods. PCR, the system will be in equilibrium in the deformed. Examine the stability by considering the further derivative of the total potential energy. Means, now I told you by energy approach also how to examine the stability. First, you need to find the first steps. You write the energy, then make it differentiations for a stationary, and from there you are able to find what is the critical loads. Okay, now you have to check whether it is stable or not. P less than PCR, whether it is stable, path is stable or not. When P greater than PCR, whether it is path is stable or not. Exactly at P is equal to PCR, whether path is stable or not. Then this path you need to examine. How to examine? You need to find higher order derivative. So higher order derivatives, if you do this higher order derivatives, okay, for a small deformations, then you will see that at P less than KL, you have a stable, unstable, and intermediate. So using a small deformation theory says something. Okay, for a small deformation theory says that if load is less than PCR, then you have a stable. When P greater than PCR, you have unstable path. Okay, when P is equal to KL, it is intermediate. We don't know the solutions according to the small deformation theory. So always the small deformation theory is not correct. Deformation theory is correct before bifurcation, before your P reach to the P critical. Before that, the solutions which you get by small deformations, that is correct, stable. Means this is correct, your path is stable, but unstable, we cannot say that. That you have to examine the large deformations, okay, which you have done here. For a small deformation, here also says that you look at this, unstable. According to the P greater than PCR, it is unstable, but it's not like that. When you did the large deformations, what you observed? You look at this. Large deformations, you observe that this is the path is stable even though P greater than PCR. So now, when P less than PCR, a small deformation is giving correct solutions. Whether path is stable or not, that will say. Okay. But when P greater than PCR, you have to perform large deformations concepts, large deformation theory you have to apply, and from there whatever results will get, that is the correct ones. Okay, so from a small, this says that is unstable, a small deformation theory, but large deformation theory which you says that this is the stable. Okay, similarly here it is unstable, but I don't know whether it is unstable, maybe unstable, but you have to ensure with the large deformations. So what exactly you have to do? Large deformation analysis. And large deformation analysis, what will happen? Again, you write a potential energy, differentiate this for equilibrium, make it, but you cannot make it your what? Cos theta is equal to 1. So you have this P is equal to KL cos theta for equilibrium. You solve for equilibrium, then you are getting P is equal to KL cos theta. For a small deformation, cos theta becomes 1. But for large deformation, we cannot make it like 1. Then you plot this P is equal to KL cos theta. Okay, so cos theta graph कैसा आता है? ऐसा आता है ना? Isn't it? 0 to 1 this side. So your graph is coming like this. This is your graph. Plot when P by PCR is equal to cos theta. This is your graph. So now you have to examine this path is stable, is it or not? How to examine that? So you have to find the higher order derivative. And once you find the higher order derivative, look at this, less than 0. Hence, it is unstable. Means this path is unstable. Okay. And exactly theta is equal to 0. It becomes because second derivative also becomes 0. We cannot able to say anything. Theta is equal to 0. Then what, if theta is equal to 0, you have to Taylor series expansion you have to perform and try to find the first non-zero terms of this pi. What is the first non-zero terms? Consider Taylor series expansion of pi at theta is equal to 0. Determine the first non-zero term of pi, and you solve this pi del pi by del theta. This all. Then you see that fourth order derivatives coming. less than 0. Before that, when theta is equal to 0, this is coming 0. This is also 0. This is also 0. This is also 0. This is also 0. Theta substitute and check it. But fourth order derivative is minus 3kl square. K is positive, L is also positive, but negative sign means this is less than 0. It means that unstable at theta is equal to 0 when buckling occurs. Since first non-zero term is less than 0, that's why state is unstable at P is equal to PCR. Okay, exactly at theta is equal to 0, yeah, at P is equal to PCR, you have unstable path. So this is wrong here. Okay, this is your stable here. By mistake, I have written unstable. This is your stable. From this to this path is a stable, but exactly at PCR, you have unstable and large deformations also you have unstable. Okay. So I'm going to end this. Okay, let us dynamic instability. I'm going to explain just through one example. Have you used swing? Everyone maybe use the swing. Okay, to maximum pleasure of the swing, what will happen? This person's supposed to sit exactly at the middle, and at the extreme ends is supposed to stand such that it should get maximum amplitude. मैक्सिमम प्लेजर या मैक्सिमम एम्पलीट्यूड के लिए हम लोग क्या करते हैं? स्विंग में जो पर्सन है उसको मिडिल में बैठना है और एक्सट्रीम एंड पे खड़ा होना है. तब then you have the, okay, in these transitions you will get the maximum amplitude. Okay, the same concept is coming here. You look at this, complete one cycle of the swing. Swing is coming from here to here, again going left extreme end, and then coming to the middle. This complete one cycle. But what about the man? Man is going to stand at the extreme ends and again sit at the middle. Half of the cycle, it complete one cycle. Again, other half of the cycle, he complete another cycle. So man will complete two cycles. Means man is nothing, it is external parameters. The external parameter will complete two cycles, and your system will complete swing. System is here, swing complete one cycle. Then you have the maximum amplitude. That example I have shown here, we relate with this column examples. In the column examples, you look at this column going from C0 to C1 when A to B. Again C1 to C0, then coming B to A. It means complete one cycle. Okay. But again C0 to C, because momentum you have in this direction, so obviously this column will go in this left direction. C0 to C2 and C2 to C0 is complete one cycle. This will complete two cycles. Loading complete two cycles. That's why I told you the frequency of the loading is twice the frequency of the column for a maximum amplitude. Okay, that is known as dynamic instability. But dynamic instability you can explain, I can explain from these figures. What is exactly dynamic instability? How it is different? This is also known as a parametric instability. And how it is different from ordinary instability or ordinary resonance. This is nothing, it is a parametric resonance. This called as parametric resonance. Why? When the loading frequency is twice, means this is twice than your structural frequency in the transverse directions. This is known as dynamic instability or parametric instability or parametric resonance. And ordinary resonance में क्या होता है? Ordinary resonance में loading you apply in this direction, the loading frequency, loading supposed to be dynamic, loading frequencies coincide with the structural frequency of the members in both the same directions. That is known as the ordinary resonance. In ordinary resonance, what will happen? At only one frequency, your system will be have large oscillations. But in parametric resonance is not like that. Parametric resonance, when you apply in plane loads, in plane frequency, in plane magnitude, loading magnitude also matters. All these three, loading amplitude, loading frequency, and a structural frequency of the member in transverse directions. will have certain combinations where structural will be, where member will be dynamically unstable. So here, this is the example of this. This V shape denote the members at this particular dynamic load. This range of frequency where a structure will be dynamically unstable. Not only one frequency, there is a lot of frequencies are involved where a structure will be dynamically unstable. When loading amplitude is 0, then exactly one point you have where twice of the frequency of the loadings, then structural frequency, you have instability, dynamically unstable system will be dynamically unstable. Okay, at one point you have when loading amplitude is 0, tends to 0. But when you have certain amount of loading amplitude, as you increase the loading amplitude, the range of frequency will be increases, and the range of frequency where structure will be dynamically unstable. Not only one frequency, but ordinary resonance, always one frequency where structure will be dynamically unstable. And loading frequency coincide with the transverse frequency of the structure in the same direction. But here, in plane, out of plane loads for ordinary resonance. And parametric resonance, you have in plane loads. Okay, loading is in plane. You have plate like this, and load is in plane, isn't it? Load you have in plane, not out of plane, isn't it? And loading, whatever is there, which is dynamic loads, and what will happen? The range, the loading amplitude and frequency, because some load is applied, which have the amplitude, which have the frequency, and the transverse frequency of the members in the transverse directions. Okay, a certain combination of these three will come into pictures where a structure will be dynamically unstable. So here, this is the loading amplitude. Here, the frequency ratio, the frequency of the transverse frequency of the member divided by transverse frequency of the loading. At this, you have the this diagram will get. Okay, this is the loading. This direction you have loading at this particular dynamic loads, and you have this range of frequency where structure will be dynamically unstable. Okay, now I'm going to this same. Let us you have a plate, and plate is subjected to in plane loads. Due to what will happen? In plane compressive loads, in plane compressive stress will develop inside, and due to in plane compressive stress, if we keep on increasing your loads, stresses will be increases. At certain point will come, what will happen? This will be deformed out of plane directions. That is known as the amount of load will amount at the amount of load at which this sudden change in the deformations from in plane to out of plane, that is known as the load is known as critical buckling loads.